We're going to start this video talking about moles. The very first bit of C5, quantitative analysis, or how much. And that is what moles are key for, working out how much stuff we have. One mole is just, or the mole is just a number. And one mole tells us we've got 6.02 times 10 to the 23 molecules. That was settled by a man called Avogadro, which means we've got 602 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 zeros. That is a lot. But actually, it's not that big an amount when we're talking about atoms, which are such tiny little things. For instance, if we go back to the periodic table and we take oxygen, which has an atomic number of 8 and a mass number of 16. Now that mass number is what we're really interested in here. This thing up here. This tells us we've got oxygen, atomic number 8. 16 tells us 1 mole of oxygen is 16 grams. Now that's really useful. We can use that. That is the basis of all our calculations. This idea that 1 mole equals mass number of grams in grams. So 1 mole weighs the same as the mass number. You can get that off our periodic table. Remember, you don't have to learn any of these mass numbers. They are on the periodic table, which is included in the exam and in the back of every single chemistry textbook ever. So, what do we need to be able to do with these moles? Well, first thing we need to be able to do, we need to be able to work out how many moles we have. And we're going to do that by first of all calculating molar masses. So we've talked about oxygen, the element, so oxygen on its own is 16. Oxygen usually gets around as O2, which tells us we've got 2 oxygen atoms joined together. So that's actually going to be 32, because that's 16 plus 16. That's our molecular mass. For something maybe a little more complicated, we might have something like sodium chloride. Same idea. Sodium, atomic mass, 23. Chlorine, 35.5 because of its isotopes, gives us a molar mass of 58.5 grams per mole. Every mole equals 58.5 grams. That is its molar mass. The mass of 1 mole of substance is the molar mass. That's key. Let's go another step further. Magnesium nitrate, it's MgNO3. Twice. So, we've got 1 magnesium, which is 24. Then we've got NO3, which is nitrogen, 14, plus oxygen, 16, 3 times, which is 16, 32, 48, plus this, 52, 62, and that is times 2 because of that there. So that's going to be 124. So our total molar mass is going to be 148, which we could write as grams per mole. So 1 mole of our magnesium nitrate is 148 grams of magnesium nitrate. Now these are all what we call relative molar masses because they are compared to 1/12 of a carbon-12. So carbon-12 is 12 grams per mole. 1/12 of that equals 1 gram per mole. So that's just a little aside, tells us why it's relative. It's actually technically compared to a carbon-12. And then we have our molar equation, the first one we need to know. You'll need to memorize this because it's not in the exam paper. The number of moles we have is the mass of the thing we have divided by its molar mass. That is a key little equation. The number of moles is the mass over the molar mass. Molar mass we work out from the periodic table. The sum of the atomic masses. This you can measure on a balance, or you might rearrange this so you get mass is the number of moles times the molar mass, and you might want to know how much you get if you've got so many moles. So remember, this mass is mass on its own. That's something you can weigh on a balance. Molar mass is something you calculate from the sum of the atomic masses. So for instance, here's an equation. Heptane is C5A and it burns with 11 oxygens to give us 7 carbon dioxides and 8 waters. How can we work out the mass of the carbon dioxide if we've got 100 grams of our starting molecule? Well, first of all, we have to work out what we can ignore. We want to know carbon dioxide, don't we? That's the question. We know this one. We know our heptane. We don't need to know about our oxygen and our water. We can ignore them. They're not taking part in this calculation. So what we have then is 1 of heptane gives us 7 of carbon dioxide. Now let's have a look. Heptane has got 7 carbons, which are 12, plus 16 hydrogens, which are 1. That gives us, handily enough, 100 grams per mole. Carbon dioxide has, in one molecule, 12 carbons, 1 times 12, so we've got 1 carbon, which is 12, and 2 oxygens, and that's all times by 7, which gives us 44 grams per mole. Not per mole. I've added these moles in, not actually correct. We know how many moles we've got from here. We assume that the numbers refer to 1 mole. So this is 1 mole of the heptane reacting to form 7 moles of the carbon dioxide. So in fact, 100 grams will give us 44 grams. That's nice and straightforward. If they'd only asked us for 50 grams, we could halve this. So 50 grams will just give us 22 grams. It's a direct relationship, there's no weirdness going on, it's just however many it is in the ratio. So that is one thing we can do with moles. The other thing we need to think about is changing mass. So, for instance, maybe we've taken some copper carbonate, CuCO3, and we've heated it. It's carbonate. Thermal decomposition of carbonate is going to give us our oxide plus carbon dioxide. Nice and straightforward equation. Say that Jamie, our example chemist, has heated 5 grams of copper carbonate and he had a mass of 3.2 grams. Can we work out how much of that we had? Well, yes, we can do a very direct calculation. That's going to be 1.8 grams. Conservation of mass says that and that have to equal. You can't create or destroy mass, so that is where that must be. So that's conservation of mass. Useful little concept. Should have come across that before. We can't create or destroy matter, so it must have the same amount on both sides. The other thing we could do is, instead of knowing how much we'd made, we could work it out. So, let's say we had lead carbonate, which is going to give us lead oxide and carbon dioxide. And we know that we're going to heat 267 grams. We want to know how much of these we're going to make. This is a straightforward relationship. For every mole of lead carbonate, we're going to make a mole of lead oxide and a mole of carbon dioxide. So let's see what we get. Well, PbCO3 is 207 plus 12 plus 3 times 16, which actually gives us 267. Nice and handy. Lead oxide is 207 plus 16, which gives us 223, and carbon dioxide gives us 12 plus 16 plus 16, 32, 34, 44. As a quick check, that's going to be 267. So conservation of mass lets us work that out. Simple ratios will be what you're asked. Last bit on our first bit on moles is to tile this together. So let's just put this up here. Moles is mass divided by molar mass. Let's say we've got this equation. Aluminium oxide can be heated and reduced to aluminium and oxygen. Question is, how much aluminium oxide do we need to make 1 kilogram? Always convert this down into grams, so that would be 1,000 grams. Well, 2 to 4, 1 to 2 is our simplest ratio there. It's just cancelled down. So for every 2 moles of aluminium, we need 1 mole of aluminium oxide. Moles is mass over mR, so mass is moles times mR. What do we need though? We need how many moles we've got. So let's keep it simple. This one is going to tell us we've got mass 1000 divided by 4 times our aluminium. Aluminium is 27. So it's 1000 divided by 4 times 27, 108. So we've got 1000 over here divided by 108. We don't need to work that out just yet because we need half of that. So, 2 moles of aluminium oxide gives us 4 moles of aluminium metal. We want to know a kilogram of aluminium. Well, let's have a look at these masses. If we work this through, this comes out at 204 grams, gives us 108 grams. That's 2 molar masses here and 4 molar masses here. So 1 gram of aluminium is going to give us 204 divided by 108, which means that for every 1 gram of aluminium we must start with 1.89 grams of aluminium oxide, which means that to make a kilogram, which is 1000 grams, we must have 1890 grams or 1.89 kilograms. Gives us 1 kilo of aluminium. So there we have it. That is the sort of thing you might want to work through. Work out how much 1 gram makes, or is made by whatever it is, and then multiply up to the number you need. So that's the mole. Next video, we'll move on to the next thing.